Welcome to the first lecture of the second part of the course, Introduction to General Relativity. The second part is intended to equip you with the mathematical tools from differential geometry and Riemannian geometry, which are necessary for working in warped spacetime. As you know by now, warped spacetime is nothing but spacetime with gravitational fields turned on. Okay, so the main reference for this lecture, which is intended to familiarize you with some key ideas from points of topology, is chapter 2 of Nakahara's text. I'm using the second edition on pages 81 to 87. Now, I'd like to preface this lecture with the disclaimer that our main aim here is to simply familiarize ourselves with the necessary concepts and ideas from Poinsett topology, which will be useful in GR, and not to become experts in Poinsett topology. Okay, that is the job of the mathematics major. So treatment will be necessarily heuristic and based in physical or geometric intuition. We won't attempt the depth or rigor of the mathematician. We will omit almost all proofs and justify our results using examples or at best simple logical arguments. And those who are interested in delving deeper or seeing more details such as proofs or more examples can consult Baum's book, which I mentioned as a general reference. Baum's book is the Dover text, and I recommend it as a general reference. Nash and Sense chapter 1 and Hawking Analysis chapter 1 are also a couple of physics or GR-oriented references which will cover similar material. And as usual, the next lecture notes will be posted on the NPTEL or SWAM website. Okay, so for this lecture, I'd assume some familiarity of elementary set theory, which is taught in high school or perhaps first year undergraduate level. If you're rusty on these concepts, you can always look up from math resources available online, such as Wolfram's Math World. At the bottom of the screen, you can see some of those. Math World or Planet Math, or even Wikipedia, okay? So I will assume people are familiar with what is the definition of a set, elements of a set, subsets and proper subsets, power sets, etc. I will assume familiarity with set operations such as union, intersection, difference, complement, and Cartesian product of sets. Third, I will assume familiarity with the concept of maps between sets or mapping between sets, concepts such as image, pre-image, domain, codomain, range, types of maps such as onto map and one-to-one map, what are bijective maps, and of course, composite maps, f of g. Most of you have seen them in high school. So, as I said, the agenda for this lecture is to introduce and become familiar with what is a topological space via the specification of open sets. Next, we will learn about features of topological spaces such as existence of neighborhoods, closed sets, closure, interior, and boundary of a set. Once we gain an understanding of these features, we can learn about some properties of topological spaces such as compactness, connectedness, and the Hausdorff-Zuckerfeld property. Next, we will introduce the notion of a continuous map between topological spaces. Now, this is a generalization or abstraction of the notion of a continuous function of single variable. So, remember, continuous function. A function is a map from the real line to the real line. And we have continuous functions. We will generalize to the case when we have a map from one topological space to the other. And we will generalize the notion of a continuous function to a continuous map between topological spaces. Once we are done with that, we will introduce homeomorphisms or continuous deformations and the notion of topological invariant. Okay, so let's begin our lecture here. So we will start with the question, why care about topology at all? Like, we are here to learn general relativity or gravity. Why do we care about topology at all? Let me remind you, topology is nothing but the most general setup to study geometry with the notion of continuity, okay? So sometimes topology is referred to as Plato geometry or geometry of shapes. So in physics, we're usually accustomed to thinking about geometry as some kind of dependent on the idea of distances and angles. But mathematicians have generalized geometry to a much more general level, which is called topology. And since gravity is nothing but the geometry of space-time, we should learn a little bit about topology. This is the main motivation, because gravity is geometry of space-time, and topology is the most general setting in which we can learn about geometry. So, the most fundamental ingredient of a topic in topology is the notion of a topological space. And how do we define it? Well, first we need a couple of ingredients to define it. First, we need a non-empty set X. So X is a non-empty set. And then we need a collection of subsets of X. So this collection of subsets is indicated by the script T. And as you can see, script T is a collection which contains these sets OIs. OIs are actually subsets of X. So these are subsets of X. And they are labeled O sub I, because I can take values 1, 2, 3. It can be a continuous value, continuous index, or a discrete index, we don't care. So long as we have this collection. And so we have a non-empty set X and a collection of subsets. Now, this collection of the subsets, when they satisfy certain criteria, they get turned into, X gets turned into a topological space instead of just a normal set. What are these criteria? Well, if the script T, this collection of subsets, is such that it contains the full set and the null set, empty set, and if arbitrary unions of two subsets which are included in script T, arbitrary union of those are also included in script T, and finite intersection of O's, which are also included in script T. So T contains if you take arbitrary number of sets which are contained in this collection, their union is also contained and the intersection is also contained. A finite number of intersections and arbitrary unions. Please keep that in mind. We allow for arbitrary unions, but finite intersections. So let me try to draw a diagram here. So this is X, and then we have a collection of subsets, which I will do. Denoted by the O's, O1, here O2, O3, so on and so forth. And union of any two is also included. So let me draw a fourth one, O4. So this, as you can see, this union of these two is included, and the intersection, which is the spindle-shaped region between the two of them. Let me just shade it here, this region, which is the union of these two, that is also included. So we specify certain open sets, and then we also include, let me just rephrase that, we specify a certain number of subsets, and then we also include their unions, arbitrary number of, union of arbitrary number of such subsets, and finite number of, intersection of finite number of such subsets. Okay, once we have that, we have converted X into a topological space. So these O's, as I've mentioned already, are called open sets, which this collection of subsets contain certain sets O sub I. This O sub I we will refer to as open sets. Some books also call them open subsets, but I will stick with the traditional open sets. And once we specify a set of open sets which satisfy the criteria 1 to 3, then we have succeeded in converting X into a normal set to a topological, very special set, which is a topological space. You can think of topological space as the most basic notion in geometry. Because we are thinking about geometry, that's why we won't call it a set, we will rather call it a space. Okay? So a topological space we will denote by X, but sometimes, to be precise, in math books you will find this pair, X comma script T. The script T is the collection of subsets which define the topology or specify the topology. And some books you will find it also T of X, script T of X. I will just use X because we will use some standard topology which is given. That's why we will not indicate, we will drop it most of the time. Okay. Now that X is a topological space instead of just a set, the elements of the set X we will refer to as points, just as we talk about points in a geometrical space. Okay. Now this idea might strike you as very abstract to you, this idea of a topological space. But actually, we can give some examples to bring the concept home. The first example is something called the discrete topology, in which we take any set X, and this collection of subsets we take to be the power set. Okay, P of X. P of X is the power set, as most of you probably already know. Power set means all possible subsets of X. So, of course, if we include all possible subsets of X, properties 1 to 3 will be automatically satisfied. So there's no big deal here. So this is called the discrete topology. If you declare the collection of open subsets to be those to be the power set. Okay, power set contains all the elements, all the subsets, not just all the elements, all the subsets of X. And the other example is that of the indiscrete topology, or coarse topology, some people call it. Now, in coarse topology, the script T, this collection of subset consists of only two elements. One is the full set, the other is the null set, empty set. So as you can see, this also satisfies all three criteria because this is what is already included, and then in union of any of these two is of course X again, which is included, and the intersection of these two is the null set, which is also included. So if I define the topology with just the full set and the null set, that is also, then X also gets converted into topological space, and the topology results is called the indiscrete topology. And these examples, although they are very easy to construct, are actually only of academic interest, and they have no physical interest as such. We don't get much physics out of them. So, but just as an academic example, we cite them. In the next slide, I will give you a more useful example. So this is called the standard topology on the real line. Okay, R. So R, you can think of R as a collection of real numbers. So it's a set which contains all the real numbers. This can be converted into a topological space if you specify certain open sets, specify a script T, which is a collection of subsets which satisfy this criteria 1 to 3. And the idea is that how do we construct such script T? We start with open sets which are actually open intervals. Actually, open sets is an abstraction of the idea of the open interval. So this is the real line R, and we take any arbitrary open intervals and we declare that to be an open set. Of course, open sets must satisfy the criteria that any arbitrary union should be. So if we take two such intervals, then the whole union and the intersection, these two are also should be included. So the idea is that one can give a topology on the real line, which is called the standard or usual topology, by considering open intervals to be the open set, as well as the arbitrary unions and finite intersections of open intervals. That will give you something which is called the standard topology on the real line. This is of immense importance, so I would hope the students would remember these. And then we can, of course, extend, if we have the real line, we can easily extend this idea to the n-dimensional Euclidean hyperplane or hyperspace, Rn. So let me just draw a little bit for R3. So this is R3, which I'm given by 3 Cartesian axes. And then how do we give R3 a topology? So R3, you can think of R3 as a set of set which contains such triples of real numbers. 3 numbers ABC, the collection of all such triplets which have real valued ABC can be thought of as R3. Now we can give a topology on this set by specifying certain open sets. And just like in the real line, we had open intervals. The way we will give open sets of R3 is via something called an open ball, which is open ball O of X comma R. That means it's let's draw around this point little x. Let me draw a sphere of radius R. And the idea is all the points inside the sphere, all the points inside here are included. So then that becomes something called an open ball. Okay. Now, by definition of this, because this is an inequality less than R, so the points on the surface of the ball are not included. Okay. Only the interior of the ball is included. So this is an open set. So you can consider all possible radius and centers. Center of the sphere to construct open sets. And then as we need in topology, we need to include the unions, arbitrary unions. So for example, this kind of, this is the union of two open balls, and of course, the intersection of two open balls, which is the eye or spindle shaped region, for example, here. These have to be also included, okay? So open balls, they're arbitrary unions and they're finite intersections. These make up the open sets of Rn, and the topology generated as a result is called the standard or usual topology on Rn. Okay, so these are two key notions you should remember from this lecture. Another associated notion is that of a product topology, and the idea is that if I have two topological spaces x1 and x2, script T1 and script T2 give the topology to x1 and x2 respectively. Then we can also define a topology for the Cartesian product of x1 and x2, which is given by the open sets of x will be given by the Cartesian product of the open sets of x1 and x2. Okay, so this will give you script T is a topology on x. So if we have two sets with two topological spaces, the Cartesian product space naturally has a topology which it inherits from x1 and x2 by taking Cartesian product of the respective open sets. Okay, so you can think one example I would give is R2, for example. R2, which we know is the plane, you can think of it as R1 times R1, right? R1 times R1, right? Let me draw it here, maybe it's better. This is R2. So then the product topology will mean for R1, we need to give an open interval and cross that with the open interval on the second R1, which is the y-axis, along the y-axis. So this gives you some kind of a rectangle shaped region, which is like an open set without the boundary being included. We don't include the boundary, okay? Because it's open interval, the boundaries of each of these are not included. So it's the interior of this rectangle shaped region. So you can have open sets which are such rectangles. And of course, we need to have unions of rectangles as well. For example, if you have two rectangles, so you need to include the union which will look something like this, and the intersection which will look like a small square like this one here, a rectangle. Turns out that the product topology of R2 and the standard topology of R2 will coincide. And you might think, how is it that possible? Because in R2 we are taking such kind of disk-shaped region, because it is R2, intersections of disk-shaped region, and so on and so forth. But the idea is that these two are equivalent because if you take a rectangle, you can always fill it out with arbitrary number of such disks, right? You can make it up into arbitrary small number of disks. You can fill out this whole thing. And similarly, if you take start with the standard topology, you can always fill it out with small rectangles. For example, in integration, we divide any particular area under the curve with small rectangles and so on and so forth. So you can always. So actually, the standard topology and the product topology for R2 or in the general case Rn, which you have n copies of R, they will coincide actually. They're not different. All right. And the last notion is that of a induced or relative topology. This has to do with subspaces. So for example, if I have a topological space X, and if I have some kind of subset inside subspace A, then given a topology on X, we can generate a topology on A. How is that possible? Well, X is a topological space. That means it comes with some specification of open sets, so on and so forth. And the idea is for the subset, the open sets of A can be generated by taking the open set of X and keeping the regions which are overlapping with A. So this will be one open set for A, this will be another open set for A, and then this region which is in the overlap of open set of X with A will give you a third open set for A, and so on and so forth. So given a topology on X, so if X and script T is the topological space, then from it you can construct a topological for the subspace A. You can convert it into a topological space with the topology script T prime, And script T prime contains the sets V sub I, which are given by the intersection of A with the open sets of X. Okay, you take these overlap regions, and it gives you a set of open sets for A. One example, prominent example is, of course, a sphere inside R3. So let me draw R3 first, and then you can consider a two-dimensional sphere. Sorry about this diagram, but I hope this. So S2 can be realized as a subspace of R3, and since R3 already has a standard topology, we can give a topology on S2. How do we give a topology on S2 is by specification of the open sets. So the open sets will be, consider some open set of R3, which will be open ball, and whatever amount it intersects on the surface of the sphere, that will give you an open set of the sphere. Okay, so this is how, starting with open sets of R3 and looking at keeping the overlap of those open sets on S2, we can generate a set of open sets for S2. So that will give you a topology on S2. This topology, which is inherited from the larger space, is called the induced topology or relative topology. All right, let's move on to the next slide. So in the next slide, we're going to introduce the notion, very crucial notion, of something called a neighborhood. Now, as you can see, without even defining a notion of a distance, we are able to define neighborhood of a point. So slowly, geometric features are emerging in a topological setting. Although it's very abstract, you can slowly see, slide by slide, that certain geometrical features are emerging. So this feature in this slide is the notion of a neighborhood. Okay. So what is the neighborhood? Well, if you take a topological space X, and let's say a point P inside the topological space, if you consider any set which contains P, so N is the set which contains P, so P is contained in N, and if this N is contained in an open set, let's say O, so N is contained in O, then that qualifies N to become a neighborhood of P. Okay, you cannot just take any set which contains P as a neighborhood. For N to qualify to be a neighborhood of P, we needed that N is contained inside an open set. Okay, and actually this is the most general case. What in math, what we prefer is something called an open neighborhood, which is defined to be any open set which contains P. So any open set O which contains P is declared to be a neighborhood of the point P. This is the larger space X. Okay, an example here I've given here is that the open interval -1, 1 is a neighborhood of the origin. That is obvious because the open interval -1, 1. So this is 0. This is contained, the origin is contained in this open interval, so the open interval -1, 1 qualifies to be an open neighborhood of the origin. So although neighborhood can be generalized, doesn't have to be open. In this course throughout, I'm going to, whenever I say neighborhood, I actually mean open neighborhood. Okay. Now we go to the next concept, which is that of a closed set, and this is complementary to the definition of an open set. A set C, a subset C of X, is closed if its complement is open. So if its complement is contained in the script T, and the script T, remember, script T contains all the open sets. So if the complement of C is contained in the script T, that is, its complement is open, then we call that set closed. Okay, so let me just draw a picture to drive the point home. X is a topological space, and let's say we have some open set O, call that O. Then whatever is the complement of this, that is called the closed set. The complement of an open set is a closed set. Okay, all the shaded region. That will be C. This is the C, and this is O. Okay, so From this diagram, you might get the impression that closed always means it is non-open, but that is not the case. And the prominent exceptions are the full set and the null set. If you look at the full set, its complement is the null set, which is also an open set. So X is closed set as well as an open set. Similarly, the null set, if you look at it, the null set is an open set by definition because we include it in every topology. But the complement of the null set is the full set, which is also an open set. So the null set is also a closed set. So the null set and the full set are both at the same time simultaneously closed and open. So this example I wanted to include because many people nurture this wrong feeling that something is closed set it means automatically implies it is not open. That is not an automatic implication. Majority of the time it turns out that closed sets do not happen to be open, but there are exceptions, and you should not think of it as, strictly speaking, a closed set is something which is non-open. It's better to say a closed set is something which is a complementary to open. Okay, so and this will become very important, very, very important in just a second when I go to the next concept. But as a homework, at this point, I would like to assign a homework in which you show that arbitrary intersections of closed sets are also closed, and finite unions of closed sets are closed. Okay, so this is these properties are just the mirror reverse image of that of the open sets. In case of open sets, arbitrary unions are open and finite intersections are open. For closed sets, arbitrary intersections are closed and finite unions are closed. Okay, and this can be very easily established using the Morgan's law for set theory. Most of you, I hope, know this. If you're not, if you're a bit rusty, you can just look up some elementary notes on set theory from the web or even the resources I cited. Okay, so as I said, the closed set means its complement is open, and it's not necessarily true that something is closed doesn't automatically imply that it's not open. So this distinction becomes very crucial in the case of connectivity. Okay, so X is a connected space. A topological space is connected if, apart from these two prominent exceptions, which are the full set and the null set, there are no subsets which are both open and closed at the same time. Okay, as I said, null set, the full set and the null set are of course both open and closed at the same time. Now, if there are no other subsets which have this property of being open and closed at the same time, then we know the space is connected. And how does it notion of connectedness, without break? We usually think of connected space as something which doesn't have a break. How does it tie in with this abstract notion of no subsets being closed and open at the same time? Again, I will substantiate using an example. Now consider the real line, which is, of course, heuristically or intuitively obvious that it is kind of connected because no space is nowhere it is broken. And consider the real line with the origin removed, pinched off. Okay, so here in the second diagram, I have R minus the origin, 0. So this one has a break. On the other hand, the real line is connected. So here we have two disconnected halves. One goes from minus infinity to 0, this open interval, and the other goes from 0 to infinity. Okay. Now, so this is a example of a disconnected space because we have the origin has been removed, pinched off. So in this case, you can check that if I consider, so these are open intervals, so they're necessarily open. Okay, these are open intervals, so these are necessarily open. But the complement of this left interval is the right interval. So the right interval, initially, because it's an open interval, it's open, but it's a complement of the left interval, so it is closed as well. Okay, so this one, this second half or the other half is both at the same time, both open as well as closed. That is why, if we have such a case, then we know that the space is disconnected. They're disconnected pieces. Okay, so this notion of closed set is crucial in defining connectivity. So it's another geometric property. So you can see how in topology, without having to introduce the notion of angles and distances, geometric things are emerging just in a set theory environment, just using properties of sets. Okay, I hope the idea of connectedness is clear.